The third talk will be given by Chunqiang from Facebook. He will tell us how configuration is managed at Facebook.
So I go by CQ. I will talk about configuration management at Facebook. Let me first start with a real story. Facebook has a performance profiling tool that can run in production. We run it in production because it can give the most accurate performance data. So at one time, we planned to run the profiling tool on the requests submitted by coming from Facebook employees. That's not a huge number of requests. However, when we made a configuration change to enable this, what really happened was that due to some errors, we enabled profiling for every single request coming from users. So you can imagine that it generated excessive amount of data. So this seems to be a trivial, naive example, but human errors do happen. That was one specific example. So more broadly speaking, Facebook released front-end PHP code into production 3 times a day. We also released back-end code for newsfeed into production twice a day. For configuration, we make thousands of live configuration changes every day. So it's 3 orders of magnitude more often than code release. And also, almost every single engineer can make live configuration changes. So these practices enable us to move fast and also encourage innovations. However, they do come with some risk. So the first problem we face is how can we manage the risk associated with change, either code change or configuration change? Internally, Facebook has a large number of systems, front-end, back-end, mobile applications. If each system uses its own configuration management solution, then it will be very hard to manage the site as a whole because of fragmentation. In addition, everything is likely to reinvent the wheels. On the other hand, if every single system uses the same uniform configuration management platform, then the requirements for performance and scale would be very challenging because we manage hundreds of thousands of servers and more than 1 billion mobile devices. These are the challenges we face. Our solution consists of 3 parts: how to write a configuration file, how to prevent configuration errors, and how to distribute a configuration file to a large number of servers and mobile devices. I will go in sequence to cover each of them. I will start with configuration authoring. Our configuration data is strongly typed. The schema looks similar to C language struct. This is one example of a configuration data. It's a pure text file. We do not manually edit the configuration file. We do not, because it's very error prone to do manual editing. This is one example of a real configuration file we use in production. This configs one component related to the storage system. So it's very complex. It's error prone to make editing because it even have nested data structure. Out of the hundreds of thousands of configuration files we have at Facebook, the median size is about 1 kilobyte. The P95 is about 50 kilobytes. So they are not small. They are non-trivial configuration files. So because manual editing is error prone, we take a configuration as code approach. Specifically, we write code to generate a configuration, and we also write code to validate that the invariants are not violated. We have a compiler that takes all this as inputs and produce the configuration file. Again, let me emphasize. We write the code to generate the configuration, and we also write the code to validate the configuration. One benefit of a configuration as a code is a code reuse. On the right-hand side, that's the very complex configuration file I showed previously. Surprisingly, it's generated by 3 lines of configuration program. It's only 3 lines. The simplicity comes from the fact that a lot of the common functions are imported from this highlighted library. You might see that I'm cheating here. I just move code from one file into another file and then claim the benefit. However, if we reuse the same library to write another configuration program, then just with 4 lines of code, it can generate a configuration file over more than 1,000 lines. Then that's not cheating, that's the real benefits. Both configuration files are real examples we use in production. I copied that from our production server yesterday. So our data shows that configuration code changes 60% less frequently than configuration files, primarily because of code reuse. So this is the real benefit. Another benefit of a configuration as a code is it helps handle code dependency. This example shows we tell one application to listen on a particular port. We have another configuration file to tell the firewall to open that particular port. These 2 configuration files have a dependency. If we change the port in one file without changing the other, the application is not going to function properly. Our solution is to put the port number in a common file and then import it from the 2 configuration programs. This is a trivial example, but in practice, you can use any code dependency that can be supported by the language, not just the constants. So specifically, we expose configuration dependency as code dependency, which makes maintenance much easier because the compiler automatically tracks the dependency, and whenever the port number changes, it will recompile both configuration programs to generate the configuration files that are consistent. So configuration as a code makes it easier to handle dependency. Then the real question is that, do engineers really write configuration programs? The answer is yes. Out of the hundreds of thousands of configuration files at Facebook, about 75% of them are generated by our compiler. Another 22% are generated by other automation tools. Only about 3% of them are manually edited. This shows that configuration as code is popular and is also effective. I just talked about how to write a configuration file. Our approach is configuration as code. Next, I'm going to talk about how to prevent configuration errors. We take a holistic approach. First, the compiler runs the validator to verify that the invariants are not violated. The engineer is also required to do manual testing for a configuration change. The tool runs fully automated integration tests in a staging environment. For example, if a configuration change that affects the front-end PHP code, the tool may run thousands of fully automated end-to-end tests to make sure that the functionality of the site is not broken. We do code review for both the configuration program as well as the generated configuration files. Finally, we run fully automated canary tests in production. Why do we test in production? The reason is because production and staging environments are never identical. There are always some most tricky problems only show up in production. So during the canary test, we typically deploy the new configuration file to a smaller number of servers and monitor the key metrics. This is automated, no human involved. If it goes well, we deploy the configuration file to thousands of servers at a larger scale. And again, we monitor the key metrics. The reason we run tests on so many production servers that have live user traffic is because some of the problems are related to performance, and they only show up when running at a large scale. If it still goes well, we will push the configuration change to all the servers globally. So the number of testing phases and the key metrics to use to monitor the health of the system, those are all can be customized. We have a flexible framework that supports testing of many different systems. So how effective is our configuration error prevention solution? We analyzed the high impact incidents at Facebook during a 3-month period. About 16% of those incidents are related to configuration changes. So previously, a book in 2013 reported that about 29% of the incidents in a system came from configuration errors. Another study in 2003 showed that the percentage is roughly about 16 to 33%. So we drill down on the incidents related to configuration changes. The pie chart on the right-hand side shows a breakdown of those 16%. About 42% are due to common errors. It means that if I point out the configuration error to you, it's likely that you can understand the error very quickly. For example, it's just due to a typo, where we use the name of a cluster that never even existed. It's just a typo. Another 32% are subtle errors. It means that even if I point out the configuration error to you, it's still hard for you to understand what's the real root cause. The reason is very subtle. Examples include performance-related issues or butterfly effects, where changing one configuration on one component affects another component several steps away. So it's not easy to understand. The next category is actually not a configuration error. It's just a configuration change expose bugs in the code. For example, when you make a configuration change, it enables a particular code path in your program, then that may be a bug. So that's about 36%. If we take that out, the real configuration errors is about 10%. So I just described how we prevent configuration errors. Next, I'm going to talk about how we distribute a configuration file globally. A configuration change is checked into a Git repository. We use the Git repository for version control, so that the repository has a paper trail of every single change in the system that can be used for debugging or for reverting the change or for any purpose. The tainer extracts the change and writes it to a zookeeper ensemble. The leader and the followers in the ensemble run a consensus protocol among themselves. So as a result, the data is strongly consistent and also highly available. If the leader fails, one of the followers will be converted to a leader. The leader also forwards the write to observers running inside every cluster. So as a result, the leader, the followers, and the observers, they all maintain a full copy of every single configuration file in memory. They only keep the latest version of a configuration file. They do not store the history. The history is stored in the Git repository. The servers in a cluster connect to the observers to fetch configuration file. When a program starts up, the program subscribes to a particular configuration file and fetch it from the observer. A server only fetches the configuration that is needed by applications running on that server. A server does not keep a copy of all the configuration files in the system. So it's different from observer, leader, and the follower. After subscription, if the configuration file is modified, the change is pushed all the way from the Git repository down to the server. And the application will get a callback in real time. So in terms of consistency, our solution guarantees that all the servers receive configuration updates in the same order. And even if a server fails after it recovers from the failure, it will still get the latest version of the configuration file. It will not miss out the update. The server caches the configuration file on disk. This provides high availability. Even if the entire data distribution infrastructure is wiped out by an outage, applications running on the servers can still continue to function using the cached configuration files, even if they temporarily cannot get updates. Some configuration files are large. They can be megabytes or even gigabytes. Examples include machine learning models for search ranking, newsfeed ranking. It's not scalable to distribute those large configuration files through the tree. Instead, we store those large configuration files in a storage system separately. Only the small metadata about those large configuration files are checked into the Git repository. The metadata specifies the latest version of the large configuration file and where to fetch the content of the large configuration file. The small metadata is pushed all the way down to the servers. Guided by the metadata, the servers run a peer-to-peer protocol among themselves to fetch the content of the large configuration file without going through the data distribution tree. This solution provides high throughput without sacrificing consistency guarantee. The metadata is consistent, which further drives the consistency of the large configuration file. This is the configuration change workload in our system. the workload grows very rapidly. The x-axis is the time. The y-axis is the number of commits per day. There are 3 curves. The one on the top is configuration change. The 2 at the bottom, they are front-end code change and back-end code change. This figure shows that the configuration data change much more frequently than front-end code and the back-end code. Moreover, the configuration data grows much faster than the change of front-end code and the back-end code. This rapid growth is the reason that Git is the bottleneck in our system, not the data distribution tree. This figure shows the end-to-end latency from committing a change into the Git repository to the configuration file reach the servers globally. The latency varies between 10 seconds and 30 seconds, roughly. 70% of that latency is actually spent in Git operations. The data distribution only takes about 3 to 5 seconds, actually very fast. So we are working on splitting the data across multiple Git repositories to improve the performance of Git. In conclusion, for configuration authoring, we take the configuration as code approach. For error prevention, we take a holistic approach, including running large-scale tests in production. For data distribution, we take a push model, and we also use a hybrid tree plus a peer-to-peer protocol to distribute large configuration files. I did not cover configuration management for mobile devices. We have a poster this evening on this topic. So if you are interested, please stop by our poster. This concludes my talk. Thank you. I would be happy to take questions.
Hi, Ting from UC San Diego. So I have 2 questions. The first one is about the configuration authoring. So I really like the idea of treating configuration as code. So my question is it possible to use the system you build to kind of manage the code and to distribute the code in Facebook? Because it seems like it's more challenging to manage configuration compared with manage code. And the second question is about the error prevention, right? So the numbers you show in the pie chart is around 30% of the configuration errors are kind of obvious, like the typos and invalid classes you mentioned. As you already enforced very rigorous checking and also review, right, and also testing. Can you talk a little bit more about what kind of errors still escape from these rigorous process and then infect the system in production? Thank you.
Oh, okay, thank you for the question. So there were 2 questions. The first one is, can we apply the same system for code deployment?
Right, it's about the difference between manage the code and manage the configuration.
Okay. So many of the ideas we use to manage code deployment and configuration are similar, like doing a staged rollout for configuration, running testing, etc. But the implementation actually are different. There are reasons for that. One reason is that for code deployment, typically there are more setup we have to do. There are other resources we have to prepare. It's not just a single configuration file we deploy there, then it would be able to run in production mode. So code has more dependency and other requirements we have to set up before we can run the code. It's not the same as the configuration. So that's one reason we don't use the same tool to manage both systems. But some of the ideas are the same. Your question is that we have done so much. but we still have configuration errors. Why? So in practice, it's a never-ending battle to fight configuration errors. One reason is because if you look at our system, doing testing depends on health check metrics. What to monitor to detect that there's any problem. The health check metrics they are never complete. There are always some of the health check metrics that we are not aware today, and we realized after an outage that I should have added these health check metrics ahead of time. We can never foresee all the important health check metrics ahead of time. That's one reason.
Got it. Thank you.
Thank you for the question.
Ananjay, Yale University. I have a question about the configuration as a code part. So what type of guarantee your compiler can achieve? For example, if I put a wrong validation code into your compiler, so your compiler can directly generate a wrong configuration file, or and the second part can check the error, or the compiler can directly tell you your validation code is not correct, and I cannot generate the configuration file for you, or what type of guarantee the compiler can achieve?
Okay. So the question is what kind of guarantee our compiler provides. We provide two guarantees from compiler. The first one is very simple, just like a C++ compiler. If there's any syntax error, you can catch that. Right? You can even catch some kind of a warning if you really improve the compiler. The second type is specific to our system. We allow the engineer to write something called a validator that captures the invariance defined on the configuration data. So the compiler also automatically runs the validator every single time before it produces the configuration file. So that's a second level guarantee we provide.
Thanks.
Hi, I'm Jonas from EPFL. I wondered if there's any way in your system to, say, tie a configuration change to a code change, or make sure a configuration change happens at a specific time, or like other constraints where you need to synchronize configuration changes with some other thing in the system.
Okay. So the question is that can we synchronize a configuration change with a code change?
Yes, or with time or something like that.
Yes. So we don't do that in our system. If you really want to ship a configuration specifically tied to your code, it's possible to pack a static configuration file into your package. For example, if you have RPM package, you can put that inside, right? So that will provide some kind of a consistency guarantee. So for us, it's actually different. We typically release code into production, even if the code is still under active development. But the code is disabled, it's not visible to the end users. And then we enable the code gradually through configuration change. For example, we will first use the configuration to enable the code for Facebook employees, so we can do internal testing. And then we will roll out to 1% of global users, and then finally to all the users. That's one example. So typically, the code will be shipped first, and then we use the configuration to manage the rollout of the code. And once we change the configuration, we do not require to do code deployment or even a code restart. It's a naive upgrade.
Okay, that sounds really clever. Thank you.
Hi, Brian Parno from Microsoft Research. Another question about the compiler. You said that you do code review both on the input to the compiler and the output of the compiler. So what are some examples of things that go wrong in the output? Is there something about the compiler you don't trust?
So there are some common errors the compiler can catch in terms of syntax, etc. For other errors that are related to the semantics of configuration, so we require engineers to define the invariance. One example I gave in the presentation is that the job scheduling priority must be a positive number. It can never be a negative number. So that's one example of invariance defined on the configuration data.
But you said you were doing code review of the output of the compiler, so that suggests that there's some property that you're not catching with your invariance?
Yes. So again, for anything that has to be specified by engineers, including invariants or like testing metrics, right? They may always have some like some ignect. We don't capture a particular error. So the code review is another level, another line of defense. The engineers will go through that manually if it's not captured by the defined invariants.
Okay, thanks.
Hi, I'm Rich Draves from Microsoft. I have a question about the canary or flighting strategy. You described several stages with like a small flight and then a larger flight and then finally a complete rollout. And I'm curious how those different stages, what fraction of errors those different stages catch. Like how often are things caught in the first flight versus the second flight versus how many errors kind of don't get caught until they're rolled out everywhere.
Okay. The question is about our canary testing stage, how we define that, and also what kind of different errors we catch in the different stages, right? Mm-hmm. So there are two stages that are most important. The first one is doing testing on, for example, even 20 servers. Actually, majority of the problems will be caught in that stage. If you have some simple errors like a crash or some resources you expect but does not exist, so you get those problems are caught very early on. The second stage is we do testing at the scale of a full cluster. That's also a very important stage because there are some software only deployed at the scale of a cluster. So in the second stage, we will catch performance problems. When the full cluster is running at a full workload, some bottleneck may show up. So the second stage will also catch fewer, but some of them are very critical performance bugs.
What are the ratios and sizes between those stages?